Have you ever turned up the volume on your speaker and noticed that the sound got louder but didn't change direction? That's kind of what happens when we multiply a vector by a real number. Welcome back, young physicists. Today, we'll explore what it means to multiply a vector by a scalar, a real number. So here's the core idea. When you multiply a vector by a positive real number, its magnitude increases or decreases depending on that number, but its direction stays the same. Let's say you have a vector representing velocity. If you multiply it by 2, you now have a new velocity vector, 2a, that's twice as fast, but in the exact same direction. The formula goes like this: magnitude of lambda a equals lambda times magnitude of a, where lambda is any real number greater than 0. This operation is vital when we want to scale physical vector quantities in equations like adjusting velocity or scaling force. Now here's an interesting twist. What happens if the scalar is negative? Imagine pushing a box to the right, that's your original vector. Now, multiply that force by -1. What do you get? A force in the opposite direction, same size, just reversed. So when we multiply a vector by a negative number, the new vector points in the opposite direction, while its magnitude is scaled by the absolute value of the scalar. For example, if vector a is multiplied by -1.5, the resulting vector has 1.5 times the magnitude and points backward compared to a. As you can see in the diagram from your textbook, vector a has two opposites, -a and -1.5a, both flipping direction and changing size. This reversal is incredibly useful in physics. We use it when dealing with forces in opposite directions or calculating recoil effects in collisions. Let's bring this concept into the real world. Say a car is moving with constant velocity. If you multiply that velocity vector by time, what do you get? Displacement. Yes, displacement equals velocity vector multiplied by the scalar time. Let's break it down. Suppose the car moves at 20 meters per second for 5 seconds. Multiply velocity, 20, by time, 5, and you get a displacement vector of 100 meters in the same direction as the velocity. This is a classic application of scalar multiplication. We combine a scalar physical quantity like time with a vector quantity like velocity to get another vector, displacement. You'll also see this in impulse and momentum equations, where multiplying force vectors by time gives a change in momentum. Scalar multiplication is everywhere in physics equations. Now let's talk about dimensions. When we multiply a scalar with a vector, we create a new vector, but what about its unit or dimension? The answer is simple. The new vector takes on a dimension that's the product of the original vector and the scalar. For example, force equals mass multiplied by acceleration. Here, mass is a scalar in kilograms and acceleration is a vector in meters per second squared. So the resulting force vector has the dimension of kilograms meters per second squared and points in the same direction as acceleration. The formula is F equals m into A, where F is force in newtons, m is mass in kilograms, and A is acceleration in meters per second squared. This dimensional consistency is what makes scalar multiplication powerful and reliable in all kinds of physics problems.
Alright, time for an example. Let's test what we've learned. Suppose a body moves with a velocity vector of 6 meters per second toward the east. What is the displacement after 4 seconds? Let's solve it step by step. First, identify the scalar. That's time, 4 seconds. Next, apply the rule. Displacement equals velocity multiplied by time. So we do 6 into 4, which gives 24 meters. That's the magnitude. And the direction remains the same, eastward. So the final displacement vector is 24 meters east. This simple multiplication shows how motion in a straight line can be expressed through scalar vector operations. You'll use this method repeatedly in projectile motion, uniform motion, and even in force-based calculations. Let's quickly wrap up today's concept. When you multiply a vector by a positive scalar, you scale its magnitude, but the direction remains unchanged. When you multiply it by a negative scalar, the vector flips. Same magnitude, scaled, but opposite direction. This operation helps us model motion, forces, and changes in physical quantities over time. The new vector's dimension is always a product of the original vectors and the scalars, preserving physical meaning in equations. So whether it's computing displacement, force, momentum, or even energy, scalar multiplication plays a foundational role in vector physics. I hope you now understand how multiplying vectors by real numbers isn't just math. It's how we bridge numbers and direction in real-world motion. See you in the next session with another exciting vector operation.